paper that is quite interested. It's from University of Twente that somehow is very simple. So in essence, it says that any packet whose size is between 120 and 220 bytes looks like DOH. This is too simple. So we have, for instance, examples in the data set that contradict this. And as you can understand, it is not very complicated to create, some traffic that looks like that, even though the idea makes sense. Okay, so because DOH, even if it is encrypted, it respects, some packet size boundaries typical of DNS. So not extremely huge packets. But this one is not going to work. At least probably it was working at the time of the paper was written, but this is not working with today's traffic. And there is also a public available dataset, that is the one from Canada. This is a good work because it contains both the dataset. The dataset is annotated, so in essence, I know what traffic is DOH, what traffic is not DOH. And it is mixed with some non-DOH traffic. There is also a paper written by this university available here at this link. In addition to that, there is another project that was presented early this year at a conference, and there is a huge data set. So this one is sponsored by the European Community. So there is a large data set just to demonstrate that the algorithm that these people were using was working. Both works are based on machine learning. Now, machine learning is working. I don't want to say that it is not the case. The thing about machine learning is that it's somehow complicated. So for instance, just to give you an idea, the number of features, so the number of characteristics that a machine learning algorithm needs for telling this looks DOH or this is not, is this one. Okay, actually there are probably a few more, but in essence this is the list. And as you can see, per se those features are not bad, but on the other hand they put quite some pressure on the probe to account them, because we need to do the median value of ratio of bars and poses, things that from the machine learning point of view make sense, but probably from the DNS standpoint are not. Just to give you an example, with DNS, you can, for instance, suppose that you have a PC at home and use DOH. So you can issue one DNS query now, then to do nothing for minutes, and then at some point a storm of DNS requests as soon as you click on some web pages. So in essence, there are some elements here that make me think that this one looks like an approach that can overfit. So if you want it to recognize a specific pattern in traffic. And also, like I said, it is a little bit complex, not extremely complicated, but not simple for sure, because it puts pressure both on the probe that is creating basically the data, and on the machine learning side that is deciding whether this traffic is DOH or not. So just to validate this idea, so we wanted to check whether this work was really working, and to double check whether it is really possible to do that with machine learning. So we have taken the Zenodo dataset, we have taken the flows labeled as DOH and those that are labeled as non-DOH, use an algorithm called XGBoost that is in essence is based on an open source library. And then all the features were used except for the data source, so the source IP, just to make sure that IP addresses were not part of the story. And so even though we can probably reduce the number of features because they are not very few, but they are about 15, 20 if I remember correctly. So just to make sure that the system is working, but like I said, probably some optimizations are possible. In order to verify whether the approach was working, we have divided the dataset in 80-20, so 80% of data was used for training and 20% for validation. And the results were pretty good, and that demonstrated that the claims of the paper I reported were correct. Also, that it's possible to create another system based on on the idea of the paper that it seems to work. So in essence, it's accurate almost 100%, just to give you an idea. And it's possible to, like you see area under the curve, to properly say this is DOH, this is not DOH. So very good. Actually, this is a great result. It's almost a perfect system. The only problem I told you is the fact that is not super simple. Okay, that still requires machine learning and requires the probe to generate some data that is necessary to feed the model. And to position this against a statistical approach that is much simpler and lighter, so we have also created a different software based on the NDPI I presented in June. So in essence, we have used those traces created by those data sets, part of those data sets. In addition to that, we have complemented with also additional traces that we have created in our systems. So putting basically Cloudflare D, that is the daemon that I told you that is interfacing DNS with DOH, or using tools such as Chrome, Firefox, or mobile phones that are already you can set, for instance, on Android the use of DOH. So somehow we have done our best to cover all the possible scenarios we have been able to to have in our lab. And the approach here was a little bit different. So because I'm analyzing TLS, in essence, in TLS, I don't know if you remember my last presentation, at the beginning of the TLS conversation, there is an exchange of client server hello, and then there is the certificate exchange. And at this point, there are a few more messages, and then the two entries, basically agree on a cipher, and then they start to talk. So in my approach, I have removed from the check all those messages that are about the first 15, 20 packets, depends on TLS version you're using. With TLS 1.3 is quicker. And so from this time on, so in essence, from the time when the two peers have negotiated the cipher, I start to use, to account the packet length, okay, of the blocks. So TLS is not like TCP, where you have to look at the individual packets, but in TLS the encryption happens in blocks. So you put in a request some information, you say now encrypted, and then once the information is encrypted, it is delivered to the other peer. So in essence, I have a look at the block length. This requires DPI to decode TLS. I mean, to decode the TLS block length, not to decode the content that is encrypted. And with only 8 blocks, this is amazing. It is possible to figure out whether we can use we can say this is DOH or this is not DOH. Of course, more blocks are desirable, but with H we have seen that the system is pretty reliable. So in essence, we have divided using binning techniques the length of this block into bins. 32 bytes long. So you said the first bin is from 0 to 31 bytes, the second one from 32 to 63, and so on. And then for every block we analyze, we increase by 1 the number of bins, okay, inside this vector. And then we normalize them so that we say, okay, on this bin we have 20% of the measurements, on this bin we have 40% of the measurements, and so on. This means that the minimum number of blocks you have to use to have some reliability is 8. But let's say if you have 20 blocks, okay, the algorithm is still working because we are normalizing, basically we are putting a percentage on the bin instead of having the absolute number of blocks that fall into that bin. And then we use some clustering techniques called k-means. Based on the data set that I found, so in essence, this is a simple, let's say, training set, I see that in essence there are 2 clusters. Okay, these are the 2 clusters. As you can see, the packet length is very low. Okay, in one cluster. But in the first cluster, there are also some packets whose size is more around 500 bytes. That's why I said, the initial paper, it doesn't work. For instance, this is a typical of Google, okay, Google DNS. So in essence, we have created 2 clusters, okay, and this is for clustering. And then for every new TLS flow that has not been classified as, let's say, WhatsApp, as Apple, whatever. So we are going to apply the algorithm. And the algorithm basically checks whether replicating this DNS algorithm of investigating and analyzing the first few blocks of the traffic, whether this one falls in one of these two groups or if falls outside of them. So in essence, using the Euclidean distance, I measure how far is one observation, so one flow from those. And based on the distance, I say, okay, this is DOH or this is not DOH. So in essence, if I can observe the traffic from the very beginning, so from the T-Wayne shaking a TLS setup, basically the system is as good as machine learning. So we have basically no false positive. Everything seems to work as good. Instead, if we are in the middle of the conversation, if we are not being able to observe the beginning of the communication, it's still working pretty well. So it's above 90%, but there are some false negative. So in essence, the system is working well from the very beginning. So it should, like a DPI, we should see the beginning of the communication, not to be in the middle of a flow. The validation has been performed using, the traffic that was used for the machine learning. That was also used by the other two papers. And this code that demonstrates that is publicly available. I put it inside GitHub, inside NDPI, so if you want to test it. So in essence, you give it a pickup file and you say, okay, what is this? And then it says, okay, DOH or non-DOH, not using DPI, okay? So DPI in this case is used only to discard the traffic that is for sure not DOH, so traffic that for instance is not TLS, is discarded. And then for TLS traffic, the algorithm is applied. And like I've said, the results are very similar to those I presented for machine learning. So in essence, just to conclude, both approaches are working, okay? They are pretty lightweighted. In particular, the statistical one is very light because we only take into account, the packet length. This code is publicly available. It's part of the, NDPI, so you can test. It's not written, like many times happens on papers and not available for testing. It's there. So we believe that, DOH detection is feasible. Again, DOH detection for services that are not, publicly available in list, because for those, APIs are already working. There are a couple of things I would like to add to this work. Okay, first of all, there is an experimental RFC called RFC 8467. So I sent a mail to the author, and he said that, okay, the RFC is out, but he's not aware of anybody using it. Because if you had a random padding to packets, so that the length of TLS blocks can increase. So this is a good way of somehow hiding DOH. So this is something that is somehow a concern, but at the moment we are not being able to find the implementation, at least in the data set that we have access to, and in our test was not used. And second, DOH implementations that are available are very few. There are not that many. So I cannot say that this system is working today, it will work forever, because probably there are other cases where DOH can hide itself in an implementation based on that. But what I'm able to tell you today is that the system with the traffic we have access to, and with tools like Firefox, Chrome, and so on, Android is detected, or more or less reliably. I mean, basically at 100% with both approaches. That's all. Thank you very much. This is the link to the source code.
Perfect. Thank you, Luca, for those sort of taking us through both the methodology and those impressive results. I'm sure we'll have some questions on the chat. So if anyone wants to raise a question, could you perhaps raise your virtual hand if you recall how to do that on Zoom, if you can. Alternately, just indicate on chat that you wish to ask a question, and we can do it from there. And whilst people are thinking, Luca, I know you, I think I saw a slide which said that for the purposes of the machine learning version, certainly you weren't relying on things like SNI rather, which is clearly advantageous if people do start to implement ECH. Was that also true for your second method, that it's purely looking at the traffic and doesn't need any other signals?
Yes, both methods don't look at SNI, but the thing is that with machine learning, okay, we have used exactly the same data set and the same data used by the other paper. I mean, if I can look at the protocol, we can reduce the number of flow labeled as DOH and non-DOH. So I mean, machine learning starts from the fact that it needs some data to build the model. So for us it was important not to discard anything, because actually we probably need more flows. But in both options, so suppose that you want to use machine learning, so we have to create first of all a probe that is able to create those features, so to report those values. And then using DPI, we can select only the traffic that can be, potentially DOH, and pass this to it. But I suggest not to use SNI. I mean, if I see DNS.Google and this is a Google certificate and so on, okay, this is DOH. I don't have to use, machine learning or statistical analysis. But on the traffic that is TLS, but that is not, a traffic that we are already able to classify, we can use, I think, DPI to somehow to filter out traffic that is not DOH and then focus only on that. I mean, for performance reasons, I think this is desirable, of course.
Excellent, thank you. So I can see that Vittorio has his hand raised. So do you want to jump in, Vittorio?
Thanks, and hi, Luca. My question is, well, I think it's $1 million question. So how easy would it be for DOH client developers to take countermeasures? I mean, I don't know if by padding or randomizing traffic or doing something they can, disrupt your detection methods.
In fact, this is the question. If you want to randomize traffic, probably you can create a problem. Actually, probably you can definitely create a problem. However, this is true, okay? So I don't want to say it is not correct, but we cannot rely on time. I mean, time was put, in the machine learning part, but I think it is not a good idea because, I mean, with DNS, time is totally random. You can issue query now forever. The thing that is the following. So while I was developing this with Daniele, we said, okay, somebody can find a good way to circumvent our tool, but in a way, if you have a host that is working and that is never issuing DNS request, and that has some TLS that looks like DOH, but you're not 100% sure. I mean, unless there are special hosts that use etc host to live, I think that there are other ways for you to detect that. So what I'm saying is that even if people don't put any random data into traffic, these are statistical methods. I cannot, guarantee 100%, even though the data set it seems to guarantee that this is DOH, because it's always possible to create some traffic that mimics DOH. So what I'm saying is that this is one approach, but there are other possible. There are some other information that's coming from the behavior of host, that at some point, it puts you focus on some type of traffic that is probably shared among multiple hosts that can let you think, okay, this looks like DOH. So what your question makes sense.
Okay. Thanks, Vittorio. See, Ralph has his question raised, and then I can see a question in the chat. So Ralph, come to you next.
Yeah, so as I know of nobody who has implemented, I think, RC 8467, but a couple of people, including us Akama, have implemented RC 7830, which is the actual EDNS padding option with kind of configurable values. Now, is the algorithm you have, would it still detect, though, if sort of one had a boundary of, say, 128 or 512 bytes, always padded to the same mechanism? Would the algorithm detect that?
Okay. Honestly, I think that we need to change something, because I don't think that it's possible to if you use padding. I mean, to add a random value, let's say, not
well,
just
it's not random. It's
if it's just a few bytes, is not a problem. I mean, if you say I want to randomly add, let's say 300 bytes, 500 bytes, depending on the packet, this is the problem. But if you just want to pad, simple padding, I don't think it's a problem, because I don't know, this is part of the query. Probably what happens is that we have to change the cluster or the cluster values to retrain the system, okay, based on those values. And for instance, so we have not seen cases where it is not working. But like I've said before to Vittorio, the thing is that we are not sure 100%. The numbers are very promising, so we are close to 100%. But these are, this is statistical analysis or machine learning, let's say. So it is not black and white. So we say this is 99.9% DOH, but it is always possible to mimic this type of traffic. Again, with DPI first, so we discard traffic that is not DOH at all. So we have to see specific TLS options, but you can really create an application from scratch that mimics this traffic. So padding, I don't think is a problem. Random, data, it is a problem.
okay. Thanks.
Okay,
Welcome.
thank you. I see Francois posed a question in the chat. What about using unsupervised deep learning methods, which is pushing beyond the boundaries of my machine learning knowledge? So does that give you sufficient to answer a question, Luca, or would it be helpful for Francois to come on and expand on that?
I think I understand. I don't know. I see Daniele, my co-author, that is online. Daniele, do you want to speak, or do you want me to answer the question?
Hello, I have no idea, because we used only XGBoost. With the XGBoost we have a good performance. So I don't know if well, we could do some tests with unsupervised deep learning methods. I don't know. Maybe yes.
This follow-up work, in essence.
Yeah. Although I guess if you're getting the sort of percentage success rate that you seem to be, then it's working anyway, which is good. Okay, thank you. I see John has his hand raised, so do you want to come in, John?
Yeah, thanks for the very interesting presentation. Were you able to notice or differentiate between different DOH stacks on the server side with your analysis, or was there any representative difference between services, whether you knew what they were running or not?
No, it is possible. At least we see that the behavior. So if you want to send me a mail, I can send you a more extensive, list. But yeah, Google, Cloudflare, Firefox, and so on somehow behave differently. I don't remember, but I think you see the first one, if I remember correctly, is Google. I'm not 100% sure. Again, if you want, send me a mail and send you the dataset. As you can see, so these are the bins. Okay, so basically at the beginning, so on the left side, you will see the first one from 0 to 32 bytes. I mean, for the TLS block, and so on. As you can see in Google, we have some length that are somehow around 500 bytes, whereas on the other implementation, we don't see them. So the implementation matters. Actually, this is a good question. It is possible to see which one it is used. Actually, there are some implementations that have very very similar patterns, but almost you can put one next to the other. Say, okay, these are the same implementation. So yes, there are some similarities in implementation, and you can find specific, at least looking at packet length, for instance, that there is some code probably is shared among 2 or 3 implementation, and other that is created in a different way. And if I remember, this is the Google one.
Which could be quite a helpful tool, I guess, if you were looking at, say, enterprise control systems, for example, where you could disable certain streams potentially if you could reliably identify the source. Okay. Thank you, John. Anyone else have any questions for Luca who wants to come in? Give you a moment just to think. And if not, to answer the question that Jim asked earlier in the chat, the slides will be shared with the notes and the call recording, and you will have seen from my message in the chat that I inadvertently forgot to switch on the recording straight away. So we missed the very start of the presentation, just Luca's introduction, but you would have got the rest of it, all the important stuff, including the results. So Luca, thank you. That was much appreciated and impressive results. Let's hope that people take a look at the code and maybe start to test it with some different traffic and see where it takes us.
Sure.
Sure.
Thank you.
Thank you.
Thank you very much. Yes.
Thank you.
Right, and on that note, that brings us then on to any other business, and I'm conscious we have, of course, IETF coming up next week. The one thing I should say before, in case I forget it at the end, I'm not planning to do a call this time next week, mainly because for those of you that are attending IETF, the time zones are such that it will make quite a long day if you want to do both IETF and then join a call at sort of this time of the day. So we'll pick up again in a week's time, or week after, I should say. Other than that, does anyone have any other business that you would like to bring up on any other topics? I see Glenn has his hand raised, so to jump in, Glenn.
Greetings. So, hey, looking ahead to IETF 109 and the very fun ADD working group, which is going to be a most excellent time for people in the East Coast United States. I'll put up the ask, if anybody on this call is going to maybe attend, I suspect a lot of people will, could we have some people volunteer to help take notes? Because notes are important, and I suspect a lot of my East Coast American parts of this group will be slightly sleepy and may not be the best note takers. So if we can get maybe somebody from Europe that's going to be awake and up would be a big help. And the other thing I'll say is, we haven't put out the agenda yet in detail about the topics, but that the format is really going to be organized around discussion. That worked really well during the interim, and I think we're going to do the exact same thing here. So in particular, getting topics onto the list in the various drafts that have been recently published. We've had some good stuff published last week, and so if you take a look at it, comment on it, see if there's things in there that we need to have further discussion on before we can move forward. That'd be really good. So we have a draft from Tommy Pauly has put out some new drafts. We've got some new drafts from other people. Chris Box has put an update to the box requirements ADD draft. So please take a look at all of those stuff. You can see which ones have been updated on Data Tracker. It's very easy. Have a comment and send them to the list, please. Or if they're on GitHub, open issues on GitHub. But that's where we're going to be mining the conversation topics for 109's ADD sessions. And there's two sessions. One's on beginning of the week. It's and it will either fall on a Monday or a Sunday, depending upon where in the world you are at when you join. One's either Sunday night for people here in the US, or it'll be Monday morning for Europe, and it'll be Monday in the afternoon for people in Asia Pacific. And then we have a second session later in the week. So please come along. We need everybody's voice to get and it's at a critical point, I think. So this is a really good time to be engaged.
Perfect. Thank you, Glenn. It should be an interesting week, albeit, as you say, for some, the time zone a little challenging. But what else were you going to do on Sunday night at 11:30? Was it 11:30, I think, or whenever?
Sleep. To be honest, sleep.
Well, to be fair, it could have been worse. You could have been on the East Coast. It would have been even less sociable. Fantastic. Thank you. Right. Well, that's a good advert for the ADD working group next week. Of course, there are plenty of other working groups and other plenary sessions running through the week. So quite a good program. And reminder, if you haven't already done so, if you want to attend IETF 109, you do need to register in advance. So don't forget to do that if you haven't done so already. and you need to apply separately if you wish to receive one of the excellent IETF 109 t-shirts, courtesy this time, I think, of Cisco, if memory serves correctly. Apologies if I got that wrong. Okay, so that was that. Anyone else got anything else that you would like to raise this week? Give you a chance to think. Again, either raise your virtual hand or put it in the chat, and I will read it out loud if you're not in a position to raise it directly. The one other thing I'll mention, perhaps while people are thinking, is sort of based on the presentation that Kenji gave last week about ECH, the notes for which are slightly delayed, but you will get those the next day or so. I think that started to prompt some thoughts from people about the implications for ECH in real world deployments. I think particularly building on the back of some of the comments from Paul and others around the use of SNI in particular environments. So I think that's something that some of us will perhaps revisit in a few conversations. So if you want to be involved in that, just drop me a line and let me know, and I'll connect you separately just to explore that in a bit more depth. That we're thinking about special environments. Paul obviously covered education. I think some of the more tightly regulated environments, such as banking and such, would be also of interest, but there may be others. So as I say, if that's something you'd like to be involved in, then just drop me a line directly. Happy to pick that up offline. So last call for anything else that anyone would like to raise this week. I'll take sort of silence as possibly not, in which case thanks again, Luca, for that most thought-provoking presentation. I'm sure that's going to get some people taking a look at the material that you linked out to, and will be certainly of a lot of interest to those people looking at enterprise tools and other network management tools in particular. So with that note, have a great week, everyone, and maybe see you at IETF 109 the sort of late Sunday, early Monday next week. So have a great week all. Thanks very much.